Hello everyone, and welcome to video lecture of chapter 31, Electromagnetic Waves or Electromagnetic Fields and Waves. This is going to be our last chapter for the semester. Congratulations, you have come a long way. Before I begin the chapter, let me go back to the Canvas course. Just a reminder, and I believe I have sent an email to everybody about the upcoming final exam. I've come up with some information on it. You could find this information under module 0 right here below the course schedule. Let me just show you the course schedule very quickly. We are currently, we have just finished the midterm exam last week, and we are currently in, we will begin on chapter 30, no, where am I? I'm sorry. We will begin on chapter 31 with electromagnetic waves, and that's going to be our last chapter. There is an associated quiz and associated homework for it. I already prepared the quiz. It's ready to go. It should open next week. Today is Sunday, so it should open tomorrow. And there is a homework as well. So that's where we are right now. The following week, we will have the final exam week, which basically, so after the 5-9. So let me give you some information on the final exam. It will open up on May 11th, which is a Monday. This is the final exam that you will have with me. And it will close on May 13th, which is a Wednesday. Here, let me show you the calendar. Here's May 11th right here on Monday. So the final exam is going to be on start on a Monday, online, of course, through Mastering Physics, and it will close on Wednesday. So you have 3 days to take the exam. Wednesday, 11:59 p.m. Okay, and the topics that are going to be on the exam are these here: Coulomb's law, which is a chapter, the first chapter, and then the following chapter, electric field, Gauss's law. Then you have electric potential. And definitely conservation of energy. I'm very big on that. And then maybe one problem on the RC circuits. And then chapters 29, 30, and 31. These are the chapters that you have not been tested on. Those are the last 3 chapters. So that's basically what the final exam is going to be, okay? The structure of the final exam is going to be similar to the midterm exam that you have just gotten, midterm 2, okay? It's going to be kind of similar to it, okay? That's it. If you have any question on it, let me know. Okay, let's go back to the topic. Please, before I begin this lecture, please make sure that you have read your reading assignment. Please read the entire chapter, or at least a good portion of the chapter, before you come and watch this video, because I am not going to explain too much details on it. Be familiar with the content before we start doing a problem. Basically, my concentration is going to be on working out problems from my lecture note and from some of the homework problems. But let me give you a brief introduction on what we mean by electromagnetic waves. Now, electromagnetic waves are basically that are transversal wave, and they have certain characteristics. But before I get into that, how did we learn about them? Well, what happened was, let me go to my notes. There it is. Okay. We have studied the following formulas. I'm going to write them down for you. The one that we have studied already. Gauss's law, E dot dA equals the charge enclosed over epsilon naught, and then this is called Gauss's law for electrostatic, or for electricity, and then there is another version for it, Gauss's law for magnetism, which we haven't covered, but it's basically the same structure except that there is no magnetic pole enclosed, so it's equal to 0. Okay, so here remember the left-hand side of the equation is the flux. The flux is equal to the charge enclosed. The Gauss's law for magnetism, the flux is, there is no such thing as a pole enclosed, because there is no such thing as a monopole. Okay, they are dipolar in that case, so they cancel each other out. So you can never ever isolate a pole. Okay, that's the meaning of it. Anyway, and the third one is Faraday law in integral form. It looks something like that. E dot dl equals to the negative change in the flux with respect to time. Again, you don't need to know those formulas. Okay, I'm just displaying them for something I'm going to talk about in a minute. And then the next one is Amperes Law, and that is, we have studied that, B dot dl equals to mu naught I, which is the current enclosed. Okay, these collectively, these equations collectively, and actually with one more equation, the one you're familiar with, is the force, electrostatic force and the magnetic force. So it becomes QE plus V cross B. Those equations collectively, those 5 equations, are called the Maxwell equations. Okay, I'm sure you've heard of the term Maxwell's equation. These are the ones. Okay, what Maxwell had done is, and for those of you who have taken Calculus 3, you may recall you've studied something called the Divergence Theorem and Stokes Theorem. Anyway, if you haven't, it's no big deal. You will study them at some point. It's advanced mathematics. You can convert, basically, Divergence Theorem and Stokes Theorem allows you to take an equation such as one of those 4. As you can see, those equations are integral equations. There is an integration sign. And you can take this integral equation and convert it into a differential equation. Okay? That's what the Divergence and Stokes theorems can do for you. Okay? Well, anyway, when you do this process, again, you'll study that when you take an advanced course in electricity and magnetism and physics, at the physics course. Anyway, you'll end up with the following version. Same equation, the same 4 equations, those top 4 equations. In differential form, they will look something like that. Del dot E equals rho over epsilon naught. Del dot B is equal to 0. And then del cross E, again, this is a simplified version of it, is negative the derivative of the magnetic field with respect to time. And then del dot B is equal to mu naught J, which is the charge density, current density, plus mu naught epsilon naught partial E partial T. Okay, these 4 equations are identical to these 4 equations here at the top. Okay, except that these are in differential form and these are integral form. So what Maxwell had done, he took those 4 equations and he combined them together. He solved them simultaneously. Again, if you take a course, an advanced course, you will actually go through this derivation yourself. And then he come up with an amazing equation, to his surprise, the following equation, which is well known as the wave equation. It looks something like that. Partial squared phi partial t squared equals to c squared partial squared phi partial x squared in 1 dimension. This is all in 1 dimension. Well, this is nothing but the wave equation, and it is well known to mathematicians for many, many years before Maxwell. So Maxwell, for the first time, he sees those 4 equations as representing electromagnetic waves. And then he took this partial differential equation, which is a function of t and x, position and time, and then he solved this equation, okay? And this phi, by the way, represent, if you ask it, phi, it could be either E or B, the magnetic field or the electric field. So I'm putting E as a phi as a general form for him. Anyway, so he took for each of them, E and B, and he solved them, and he comes up with a solution to that wave equation, and he comes up with the famous equation that we're going to be studying this in this chapter, and that is E is equal to E naught, and I believe we use let me look up your book, because some books use sine, some books use cosine. Both are perfectly equivalent. It's just a matter of taste, really. So let me Oh, Maxwell's equations are on page 887, if you want to look it up. But let me see what your book uses, sine or cosine. Sine. Okay, good. I like sine. Okay, so he comes up with this. So E equal E naught sine kx minus omega t. I'll come back and explain all that, what that means. And then B equals B naught sine kx minus omega t. In some books, you will find it to be cosine kx minus omega t rather than sine. They're both equivalent. There's no. It's just a matter of taste. But anyway, that's the one that's the one I'm used to as well. Sine, the sine function. So what that means is the following: is that electromagnetic waves, the reason we call them electromagnetic, they're basically two waves. Okay, one is electric wave. The other one is a magnetic wave, and they are both orthogonal to each other. Orthogonal means perpendicular to each other. In other words, I can't draw it in. Let me show it to you in a picture. I can't draw it with my hand. Yeah, I'm going to go to section 6. There is a picture there. Or maybe I could just use the web. Let me go to the web. It's probably faster. Electromagnetic. And then I'm just going to go to images. There we go. This is probably a cool picture right here. Look at that. So as you can see here, if you imagine the red wave here is a magnetic wave. Yes, it's a magnetic field or a magnetic wave. Both of them, by the way, are sinusoidal, which means they can be described by a sine function, and that's why I'm using the sine function here, because they're a sinusoidal wave. So anyway, whoops. So this is the red one is the magnetic wave. Imagine it that it's horizontal along this line, whatever it is. And then you get the blue wave right there, riding it. They both merge into each other, and they're both perpendicular, as you can see, to each other. They make 90 degrees. This 90 degree, we call it orthogonality. So they're both orthogonal to each other. And they're both moving at exactly the same speed, and that is the speed of light. Okay? This is called the direction of propagation, or the pointing vector. We'll talk about it in a second. Okay, so the speed here, this arrow here, is basically c, the speed of light. Okay, that's the direction of propagation, s vector. Okay, so that basically, so of course you have a wavelength which is from peak to peak or trough to trough, whatever. They both have the same wavelength, which is magnetic wave or electric wave. They would have the same wavelength, same frequency, and of course the same c, the same speed. Okay. And of course, in the electromagnetic, you have, this is the electromagnetic wave. You get gamma ray, X-ray, UV ray, infrared ray, microwave, FM, AM. These are radio waves. And then you have long radio waves and so on. And then right in between IR, infrared, and ultraviolet, there is this very thin spectrum here, is what we call the visible spectrum. We call it visible because our own human eye could see them. Nothing else. There's nothing special about them. We just happen that it happened that our eyes are sensitive only to this region in the spectrum, so we are able to see those colors. Okay, what we refer to as colors. Okay, okay. Let's go back. Okay. So let's begin. This is basically an introduction, what we are about to study. Now we define something called the pointing vector, okay? Pointing is the name of a physicist. I don't remember his first name. And it's called a pointing vector, and it is the vector S, okay? S vector. What is the pointing vector? Well, S is defined as 1 over mu naught E cross B. Okay? So this is the electric field, and that's the magnetic field. If you cross them together, we're going to be doing a lot of cross product in this chapter. If you cross them together and you divide it by mu naught, the permeability of free space, you will get what is called the S vector. Now, if you, for a minute, for just a minute, imagine that you would ignore the mu, just to ignore it completely. So what you are seeing here really is that S is equal to E cross B. All right? So what that means, if I have, for example, here is X and Y like that, let's say this is X and this is Y and this is Z right there. Okay, and let's assume that, I'll change the color again. Let's say for example, the E is this way. This is the E vector, okay? And here is the B vector. Okay, so E cross B, it's going to give you a vector going this way, right? Use your right hand. And that's basically what we refer to as the pointing vector S. You see what I'm saying? That will be the pointing vector. And it's basically, it's E cross B up to a constant, 1 over mu naught. Okay, that's basically what it is. So 1 over mu naught. Now, here is some, more on it in a second. If you remember from last chapter, also from your reading, if you start reading the beginning of the chapter, when Maxwell was analyzing those waves, he discovered the following relationship, that the speed of light is equal to 1 over the square root of mu naught epsilon naught. This is an important relationship that you want to keep in mind. So epsilon naught is the permittivity of free space and mu naught is the permeability. If you plug in those numbers, you know, epsilon naught would be what, 8.85 times 10 to the negative 12, and mu naught is, 4 pi times 10 to the, 10 to the negative 7. You plug it in, take the square root, take the reciprocal, you will get the speed of light, which is 3 times 10 to the 8 meter per second. Okay, pretty amazing result, really, if you think about it. You have those two constants, it will give you exactly the speed of light. Okay, that's one relation that you want to keep in mind. The other one that also, as a consequence of Maxwell's work, is that, which is something you've seen last chapter, is that E equal to CB. Okay, I know you've seen it before. So this also comes as a consequence. Also, it comes also even for in terms of amplitude, like what you're seeing here. See, E naught and B naught is the amplitude of the wave, right? Let me go back to the picture. Did I keep the picture? I didn't keep the picture. Oh, well. Anyway, so these are the relationship. Just box them for now if you are following my notes. And when we start doing problem, you'll see how useful they are. Okay. So with this in mind, so let me go back to the pointing vector again. It's right here. Let me write it in scalar form. Right, and remember that C is square root of mu naught epsilon naught. If I square both sides, I will get C squared equals mu naught epsilon naught, or I can say that mu naught is equal to 1 over C epsilon naught, C squared epsilon naught, sorry. Right, so that's one identity to keep in mind. So from this, with those relationship, I can say, oh, and of course this one as well, okay? So I can write S to be equal to E times E over C mu naught. Is that okay? And that'll be equal to E squared over C mu naught. Is that okay? And from there, I can also write it as C epsilon naught E squared. You prove it to yourself. So that's another relationship that you want to keep in mind. So you have this relationship, we have this relationship, and this one. Okay, there's a lot of them. Now, another thing is what I'm trying to say is, what is the pointing vector, beside the fact that it gives you direction? Well, the pointing vector also gives you information about the intensity of the wave. The intensity. Wave. Okay. Now let me talk about intensity, and I'll come back to the pointing vector. Intensity, I don't remember if I talked about it in class or not, but intensity, the definition of it, is equal to power over area. Okay. So, for example, if I have a source, say a light source. So let's say I have a flashlight right here, and here's a light. And let's say, for example, the light bulb, this light bulb, has a power of, say, 75 watt. Okay? And let's say I am measuring the brightness at some distance r right here. Okay? This brightness is what we refer to as the intensity. Okay? So what is the intensity? The intensity equal to the power that is given off by the source, which is 75 watt, okay, divided by the area. Area of what? Well, it is area of the spherical wave. See, that is, you can think of this this power source is emanating spheres, you know, one sphere after another, spheres like that. Okay, infinite number of spheres. Well, the sphere that comes here has a certain intensity, you know, I, and it has a certain area. Well, what is the area of the surface of a sphere? If you remember, 4 pi r squared, where r, the distance here is r. So in this case, the intensity, we define it as the power over 4 pi r squared. Okay, this is a very important relationship. You got it? Okay. Now, the way we represent electric field and magnetic field is with this relationship, the one I have just written just a minute ago. E equals E naught sine kx minus omega t. Now this k, this k, we call it the wave number, and it is equal to 2 pi over lambda. Okay, omega here is the angular frequency. And it is equal to 2 pi f. F is being the frequency, you know, the number of cycles per second. Okay, or if you want, is equal to 2 pi over tau, the period, right? So I can write this, the way your book writes it is this way. E naught sine 2 pi parenthesis x over lambda minus ft. Okay, it doesn't matter which way. Now, if I ask the question, what is, I mean, first of all, if I want to draw this, how is it going to look like? Well, it's basically a sine wave, so it's going to look something like that. I'm sure you remember how to draw a sine wave. Approximately, something like this. And so on, okay? Now, of course, the height of it is going to be what? E naught, right? Now, if I square both sides, which is kx minus omega t, right? And I'm going to draw it on the same graph. It's going to look pretty much the same thing, almost like that. Roughly, okay? I mean, you can use a calculator and prove it to yourself. It will actually be almost the same graph, except you don't see the negative side here, okay? You're not seeing it. Why? Because it's sine squared, right? Which means it's always positive. So basically what will happen is that you could think of like, you take this part, which is below the x-axis, and you actually lift it up, okay? And the one that is lifted, it just stays there, okay? So you basically get this. Now, if you take the average value, if I ask the question, what is the average value of this thing? Of E squared, that is. It turned out to be, if you actually do the mathematics, is actually equal to 1/2. Half of the original value. Okay? You can actually prove it by doing the following. Well, hold on. So what I'm interested in, we said that S is equal to one of the relationship that I showed you. Let's take one of them. Let's say we want to take this one here, E squared over C mu naught. Okay? So if I want to take the average value of this intensity, this is an intensity. So I want to take the average value of it, S bar. So what I'm going to do, I'm going to be taking the integral from 0 to tau, which is the period, dt. I have already done that. I know that the average value of E squared, in other words, if you take the integral, it will be half the maximum. Whoops, I forgot to write that. This is half the maximum. Okay, that's the average value. In other words, E squared average is E naught squared over 2. The average is half of the maximum. You got that? Okay. So in this case, when I do this one here, well, this is just a constant. So I will get basically the same result. In other words, the average value of the pointing vector is equal to E naught squared over 2, 1 over C mu naught. Okay? Okay. Why am I saying all of that? Well, the average value turned out to be equal to the intensity I. So the intensity I, which we said it's equal to the power over the area, is also equal to the average value of the pointing vector. Okay? And of course, the pointing vector has many different forms. Here is one of them. So it's equal to 1 over 2c mu naught E naught squared. Remember, this is E naught squared, not E squared. This is basically half the amplitude, half the maximum value. Another version for it is C epsilon naught over 2 E naught squared, and so on. Okay? All right. Let me give an example and show you all of that. I'm basically done with the theory. This is basically how much I want to. You can read more. This is just kind of a brief summary of what the theory is all about. And now I think I'm just going to start working on some problems. So let me start with example 31.4. 31.4. I always forget that I have the book here. First I need to find it in the book, in the hard copy, so I can locate it easier. 31.4. Sorry, give me a sec. There is a lot of pages of just nothing. Page 894, and that's section 6. Five, 6. Is that it, really? Is that 6? Oops, that's 5. Properties of electromagnetic wave. There we go. It's also almost the end of the chapter. Okay. Here is the pointing vector right here, okay? And here's the difference. This is what we have just talked about. So he's talking about it in this part right here. So here's the electric field, magnetic field. Here's the pointing vector, which is basically the direction of propagation. And then here's the pointing vector in a scalar form. So you get those different versions for it. And then the intensity, power over area, or the average value, I like to call it S bar. He calls it S average. Here is the expression for the electric field, okay? And then the average value, you square both sides, and you get a half. There we go. Okay, this is half the value of the amplitude. Okay, and there we go. You get this, and there we go. Okay, so I wanna do this example. Let me move it to the side without moving it off the screen. It should be here. Okay, it says a digital cell phone. This is an easy problem. A digital cell phone broadcasts 0.6 watt signal at a frequency of 1.9 gigahertz. Okay, write down what's given. what are the amplitude of the electric and magnetic field? He wants basically E naught and B naught. Okay, not E and B, E naught, like this one here, E naught. What is the amplitude of the electric and magnetic field at a distance 10 centimeters from the distance to the center of the user's brain? Okay, or about the center of the user's brain. Okay, so basically what you have a cell phone, and the power on the cell phone, or the broadcasting power, is 0.6 watt, and the frequency is given off is 1.9 gigahertz. Okay, and of course here is the human head. That's his eyes, and here is the phone right here. He got it to his ear, right? So it is about 10 centimeter distance to the brain. Okay, so he wants to know what's the electric field or magnetic field affecting the brain, if you will. That's basically what he's saying. Is that what he's saying? I think it is. He said, what is the amplitude, the maximum value of the electric and magnetic field at a distance 10 centimeter, about the distance to the center of the user's brain? Okay, let's calculate that. So how do we do it? Well, first of all, I can always calculate the intensity. The intensity is power over area. Okay. And the area here, basically, so here is the phone, and let's assume, forget about all of that. Here is the head, right? So let's say I'm interested in finding the intensity at this point right there, okay? Right here. So how do I find the point, the intensity? Well, look at it. Here is the phone, so here is the radius. So there is, remember I told you about that, I'll put a different color. So there is a sphere, spherical wavefronts. I can't draw the sphere right here, okay, of this radius r. Okay, so that would be, this area here is the area of the sphere. So in this case, so you have power over 4 pi r squared. You see what I'm saying? Plug it in. 0.6 4 pi r squared, r, he said 10 centimeters, is 0.1 squared. You calculate that, and you'll end up with 4.78 watt per meter squared. So there we go. That's the intensity. Roughly 5 watts per meter squared. Okay, fine. But he's asking for the electric amplitude and the magnetic field. Well, we know that I is also equal to S bar, and S bar is equal to what? There are so many different, go back to the notes. One of them is this one, C epsilon naught over 2 E naught squared, whichever one you want to use, but that's one of them, right? So I can easily solve for E naught. So it becomes 2S bar over C epsilon naught under the square root. Plug it in, right? Remember, this is S bar. All you need to just plug it in. So you have E naught is equal to 2 times 4.78 divided by C, 3 times 10 to the 8, and epsilon naught is 8.85 times 10 to the negative 12, and then all of that under the square root like that, and then you calculate this, and the answer would be 6 volt over meter. Okay, there it is. That's the amplitude. That's the maximum amount. Now, what is the magnetic field? Well, we know that there is a relationship. E naught is equal to CB naught. You see that? That's why I told you those relationships are important. Okay? All you need is just to solve for it. So B naught is E naught over C. So that's 60 divided by 3 times 10 to the 8. And that will give me 2 times 10 to the negative 7 Tesla. Okay? Easy? Okay. All right. One more. Oh, yeah. Let's do some homework. There are some tough problems in the homework, I think. Let me start with number 17. I'm using my hard copy here. Let's go to the book. Show it to you. Homework. let's start with 17. Some of them are a little bit hard in the sense that they require knowledge of vectors. And you are expected to know this material. Is that the one? 17 right here. Is that the one? Yes. Okay. It says a radio wave is traveling in the negative y direction. What is the direction of E at the point where B is in the positive direction, positive x direction? Okay. So the first thing you need to do, you need to draw this thing. You couldn't understand without making a drawing of it. So let's do that. Actually, this is not a bad problem. That's not the hardest one, the one I was thinking of. All right, so let me draw a 3D, a three space, X, Y, Z. Okay, and this is X, this is Y, this is Z. Okay, let's read it again. I'm gonna start putting the vectors on it. He said radio waves traveling in the negative x y direction. Negative y direction. What is that? What is he saying? What is it? Is this electric field or magnetic field? It's neither. It's what? It's the pointing vector. Got that? See, it is the pointing vector is a vector that tells you what the direction of the electromagnetic, both of them. Okay, the direction of propagation. Okay, so the pointing vector is the direction of propagation, besides the fact it's also intensity. So what is the negative y? It's right here. I'm going to try my best to draw it right here. This is the negative, so the direction of propagation is going to be such a lousy drawing. Hold on, let me try and do it better than that. I'm trying to orient myself to make it a better drawing. It won't, hold on, sorry about that. Oh, Lordy. I'm going to do it all over again. You know, I could never learn how to use that stylus pen. But anyway, okay, let me make it block like this, so maybe easier for me. Yeah, that'd be easier probably. Okay, so if I say this is X, Y, and Z, this will probably be easier. What I'm trying to do is that this is the negative, so therefore, maybe I'll change the color. How about that? I'm sure you probably, some of you are laughing at my stupidity with this. There we go. So this is the pointing vector. Got it? Okay. Okay. It's a radio traveling in the negative y direction. Okay. What's the direction of E? He wants E at the point where B is in the negative Z direction. Excuse me, is in the positive X direction. Well, here is B right here. Remember that X, Y, and Z are mutually perpendicular. All of them, always. You got that? They are mutually perpendicular, mutually orthogonal. Okay, they make 90 degrees with three of each other. But the order is important. It is E cross B. So it is E cross B gives me S. You know, the right-hand rule, E cross B gives me S. Okay, so with the right-hand rule, I'm assuming that you know how to use the right-hand rule, I hope. So E cross B, well, where would the direction of the electric field be in order for S to be in this direction? It turned out that it's this one. It's actually in the negative Z direction, this way. Okay? Let's say you don't believe me. All right? Let's assume you don't believe me. Let me show you how you can do that. How can I prove it to you mathematically without any pictures? What's the definition? Well, how S, E, and B are related? Well, S equal to 1 over mu naught E cross B, correct? Well, let's put in the vectors. S is what? Is minus Sj equals 1 over mu naught E, I don't know anything about it. Cross B. B is what? Is BI, right? You got that? Okay. So, what vector, I use the mouse, what vector E, I cross it with I get negative J. That's a math problem. That's a purely math problem. Okay? An ambiguous vector, here is a general problem. An ambiguous vector, let's call it V. You cross it with I, you get minus J. So what is that vector? Okay? So one way to do it is, remember the IJK, the one I call clock? Looks like that. IJK. What that means, I cross J is K. K cross I is J. J cross K is I. Okay, that's a cool thing to learn, to keep in mind if you don't know it. Okay, so now I'm asking, go back to this one. An unknown vector, you cross it with I, here is I, you want to cross it with I, you get negative J. Well, look at this. K cross I, it'll give me J, but however, since it would be minus K cross I, will give me minus J. See what I'm saying? So basically what it is, which is what we have in here. So in this case, I will have E is equal to minus E K vector. So, I mean, to me, I can find out about it quickly with my right hand, using the right hand rule from the graph itself. Or you can do that analytically like that. You can use the vectors itself, the cross product, your knowledge of a cross product. You have this in mind. What vector I cross it with I get negative J. Basically, you need to look for it. Well, it's just negative K. So, anyway. All right. Next problem. Let me do number 21. I'm not sure what it is. Yeah, let's do it. Number 21. There we go, right here. It says a 200 megawatt laser pulse, okay? 200 megawatt laser pulse is focused with a lens to a diameter of 2 micrometer, okay? Question, what's the laser beam's electric field amplitude, E naught, at the focal point, okay? B, what is the ratio of the laser beam's electric field to the electric field that keeps the electron bound to the proton of a hydrogen atom? The radius, you can do the second part. The second part is not difficult. I want to do the first one. So what we have in here is that we have the power is 200 megawatt, which makes it what? 2 times 10 to the 8 watt, is that right? And then we have the diameter, 2r, equal to 2 micrometer, and that's the radius means is equal to 10 to the negative 6 meters, right? And he's asking for, I forgot what he's asking for. What is the laser beam electric field amplitude? He wants E naught. He wants E naught. Okay. Again, first thing that comes to mind, find the intensity, S bar, which is power over area. In this time, the area is not an area of the spherical wavefront. It's more of the area of the cross-sectional area of the beam. See, here is the laser gun, whatever it is, okay? And here is the laser beam. Well, the laser beam, that cross-sectional area of the beam, this area, you see what I'm saying? Well, that's just pi r squared, the area of a circle. You see what I'm saying? That's really what he's looking for, or what he's talking about. So here we have the power over pi r squared, not 4 pi r squared. Okay? Or rather, we are using big R, so I'm just going to call it big R. So in this case, S bar is equal to 2 times 10 to the 8 watt divided by pi 10 to the negative 6 quantity squared. And then from this I can solve it. Let me use my calculator. So I have here, I hope you're working with me. So I have 2 negative 8, oops, sorry, repeat again. 2 to the 8 divided by 3.14 divided by, if I did it correctly, answer 6.37 times 10 to the 19 watt per meter squared. That's really large, right? Okay, now we know that S bar, again, you have different versions, pick the one you like. C epsilon naught E naught squared over 2, and we are solving for E naught, so that's 2 S bar over epsilon naught C, did I do it right? Under the root like that, and then you just plug it in. And when you plug it in, you'll get 2.2, I'm just jotting the answer for my notes here, to the 11 volts per meter. There we go. You got the answer, right? Okay, that's part A. Part B, he said get the ratio of the laser electric field to the electric field that keeps the electron bound to the proton. All right, I'm not going to do the whole thing for you, but here is how it works. Here is the hydrogen atom. Here is the electron. Here is the proton right here, right? Here is the Bohr radius. Okay, and the Bohr radius is 5.29 times 10 to the negative 11 meter, I think. He gives it to us. No, I think so. Negative 10, 11. Yes, it is. Okay, and then so all you need is just to calculate the electric field here, right there. Well, that's just K E over R squared, where R being the Bohr radius. Calculate that number. Okay, you have everything. Calculate that number, and then you take that number and you get the ratio with this number. In other words, E over E naught, and that's basically what he's asking for. Okay. Okay, good. Now we come to a problem that you may find it difficult. There's a lot of vectors in it, and I like this problem. I usually solve it in class, and I take like almost a third of the lecture just talking about it. So I'm going to solve it. I believe it's a homework problem. Make sure you pay attention to this problem. Now, if you are able to solve this problem without looking up the solution, you really understand vectors. Okay? You may not understand this chapter, but you really understand vectors. So let's dig into it. There are other problems similar to it. Anyway, so that's problem number 28. I believe it's homework. Oh, let's go to the book and show it to you. There's a nice picture to it right here, okay? There are similar problems to 28, by the way. It's 29, 30, and 31, okay? These are all maybe 32 as well. So those are maybe those are problems that you want to practice before the final or something. And I think number 28 and 30 are homework, I'm not sure. Anyway, let me magnify it a little bit so you can see the picture of it. Right here. Okay. Look at this picture. So here you have the magnetic field going to the right this way, and then you have an electron, okay, and there is a net force, this red vector is a net force on it. He said, what are the electric field strength and direction at the position of the electron in the figure? All right. In addition to that, he said moving out of the page at 10 to the 7 meter per second. So this electron is actually moving out of the page, okay, towards you, towards your face, if you will. Okay, it's moving. So we want to know what is the electric field. He gives you the magnetic field, B equal 0.1, and the direction of it is in the positive x-axis, if you will. But what is the direction of the electric field? That's what he's saying. Remember, basically, let me explain it better. Imagine you have a region in space where there is a magnetic field and an electric field. They're both there. Let me explain it. Let me explain it in some pictures before I go into this problem, because from my experience solving this problem, students don't understand what the problem is asking for. Okay, forget about this problem for a minute. Imagine there is a region in space where, let's say, here is the magnetic field. Okay? And let's say there is also an electric field going this way. I'm just guessing, completely guessing direction here. This is electric field. All right? And they have angle theta between them, whatever, okay? So what I do, I take in this region of space, now what I do, I shoot a proton inside. Now it comes in. So here is the proton right here. Okay? And it's moving, let's say, in this direction. The question is, while it's moving, it's under the influence of what? It's under the influence of the electric field and under the influence of the magnetic field, right? So how is it going to behave? Or in other words, what's the net force on it? Remember, because it's a proton, you have an electric force, Coulombic force, equal to QE, right? And it also is under the influence of a magnetic force equal to QVB, QV cross B. With those two combined, the proton is going to move off in certain direction, or there is an associated net force on it. Let's assume hypothetically it's this way. Totally a guess, okay? Here it is. This is the net. Where did this net come from? It came from those two. In other words, F net is really equal to the Coulombic, this one, plus the magnetic field. Like this. That's really what's happening. Do you understand the question now? He didn't explain any of that. He just kind of gave you that one sentence, and then he let you on your own try to explain it. But that's basically what the story is. Given a particle, I throw the particle, I place the particle with a certain velocity in a space or in a region where in that region there is a magnetic field and an electric field, either both or each of them has its own direction. They could be orthogonal to each other, they could make an angle, whatever, okay? And then how the proton or electron or whatever subatomic particle you deal with, how that charge is going to react. In other words, what would be the net force of that charge due to those two electric fields? Got it? Okay. And that's why we write this equation, which is the fifth equation of Maxwell's equation, if you remember. But anyway, so back to our problem now. This is basically what we have here. So let me make the drawing first. Here is a picture. I'm going to draw it, and then while you look at it, it's right here. I think it's not outside the video screen, that is. Shouldn't be. I hope not. Okay, so here is a picture. I'm going to draw slowly. This is the magnetic field. Look at the picture and compare it to how I draw it. Okay, and I have an electron right here, and the electron is moving with a velocity out of the page equals to 10 to the 7. It's given to me in the problem right there. Right there, see it? And then I have a magnetic field, B, equals 0.1, okay, 0.1 Tesla. Okay? And the net force, I'll put a different color. The net force, red. The net force on this electron is in this direction, like that, with a force F. That's the net, remember. This F net, it gives you a number. It's equal to 3.2 times 10 to the negative 13 Newton. All right. Now he's asking for, what is the electric field? The electric field is not shown to us. but we want to find it. In other words, what is the electric field direction and magnitude to produce a net force of that F, that red colored F, okay? In addition to that, he gives us also the angle, 30 degrees. Okay? So how do we do it? Well, all right. I'm going to begin with this equation right here. Okay, this equation. All right. So I have F equals to QE plus QV cross B. But before I do that, I know that this F is also has two components, right? IFX and JFY. Well, what is IFX and JFY? Well, that's equal to I. Go back to the picture. The picture's right here, guys. Look at this picture right here, okay? So IFX would be what? It would be F cosine, oops, with a minus. Cosine 30, right? Plus J F sine 30. Is that right? So that's going to be minus 0.866 Fi plus 0.5 Fj. So far so good? You know, cosine 30 is 0.866. Now I'm going to take this thing and plug it back in here. And before I also, one more thing. What is B? Well, B, look at it. If I assume here is my coordinates, you have to establish your frame. So if this is X, this is Y, and this is Z, then B here is basically I. Make sense? And the velocity V is K. Yes, it's out of the page, so it got to be K, right? Okay, this is important. Now I go back and plug all of that stuff into my master equation right here. Okay, so let's do it. That's going to be, again, this F right here is this, the one, the last step right here. So that's just going to be, let me write it properly first. It's got to go something like this. I negative 0.866 F plus J 0.5 F equals to, remember it's an electron, so the charge Q is E, so it's just going to be E. E, I don't know anything about E, so I'm just going to leave it the way it is, the big E that is, plus E, V. What is V here? V is 10 to the 7 K cross B. B is what? 0.1 Tesla I. There we go. Got it? Okay. Next step, I mean, F here is given to me, the number. It is 3.2 times 10 to the negative 13. So I can plug all of that stuff in and multiply by 0.866 and 0.5. I'm going to end up with the following. I already solved this problem. I have it in front of me. So it's going to be minus 2.77 times 10 to the negative 13 I plus 1.6 times 10 to the negative 13 J equals to EE, right? Minus or plus? Minus E, and then what is K cross I? Let's see. Here is the IJK. K cross I, so it's going to be K cross I will give me J, correct? So that's just going to be J, and then 10 to the 7 times 0.1 is just 10 to the 6, so that's going to be E 10 to the 6 J, correct? With a minus. Why the minus? Anyone tell me? I wish I was in class and I will hear your answer to that. The reason is because, you remember, you have the force, the magnetic force, QVB, but if it's a negative charge, you flip it. Remember, they flipped the force, remember? So for a, if it's a positive charge, it's QVB, you use the right-hand rule. For a negative charge like an electron, you use the right-hand rule, but whatever result you get, you're going to flip it, right? So you have, that's why you have to put that minus sign, because it's flipped. You got that? So it has to do with the right-hand rule. Anyway, we got that. And I hope you already see we are almost finished with the problem. The hard part is setting it up. So anyway, now I know that the value of E, 1.6 times 10 to the negative 19, we can work it out. And then when I do that, I'll end up with the following. Here's a trick for you. Since I have here 10 to the negative 13, I'm going to multiply everything by 10 to the positive 13. So I'm going to end up with this. Negative 2.77 I plus 1.6 J equals 10 to the 13 EE minus 1.6 J. You work it out and prove to yourself that what I have done is correct. I'm sure it is correct because I've done it only a million times. And then this is just a number here. And then you reduce it. Okay, you move this 1.6J, you move it to the other side. It will end up adding up with this one. And then you keep working on it. And then you solve for E by itself. You end up with the following. I'm going to skip some steps here. I will end up with this. Negative 2.77 I plus 3.2 J times 10 to the negative 13 sorry, there's an E here, okay? And then anyway, the final answer is this. So when you do it, the final answer is negative 1.73 I plus 2J in parentheses times 10 to the 6 volts per meter. And there we go. That's the final answer. But the hard part about this problem is how to set it up, how to get that vector equation starting from here, starting from this star equation. And how do you see all these vectors? How are they playing a role? How do they come excuse me, how do they come together? Okay, that's the hard part. And then you get the vector, the vector algebra that you have to analyze. Okay, I hope everybody got it. One more problem, and I think I'm gonna finish this lecture with this one. Number 42. Please work on number 30 and number 30 and 29, and let me know if you have any questions on them. I'm going to do number 42. I believe also is homework, and then you can work on the rest. There is number 61. It's pretty cool. I don't know why you put it level 3. It's not that difficult. Again, work on it and let me know if you have a question on it. All right, I'm going to do number 42. That's going to be the last problem I'm going to work on today. Oh, we have the book here. Okay, it's right there. I can make it a little bit bigger. Okay. Says at one, it's more of a math problem really, but anyway. Okay, it says at one instant, the electric and magnetic fields at one point of the electromagnetic wave are, then he gives you the expression for the electric and magnetic field. So E is equal to 200I, 300J minus 50K volt per meter, and B equal B naught, okay, that's an unknown, 7.3I minus 7.3J plus alpha K mu micro Tesla, okay? First thing he said, what are the values of alpha and B? Okay, so you want the value of alpha, which is a constant, and the B value, okay? And then what is the pointing vector at this time and position? Well, how do we find the pointing vector? You remember, right? It's the cross product between E and B. right? 1 over mu naught E cross B, you get the Poynting vector. Okay, but let's worry about part A. What are the values of A and B? All right, let me just first always write down what's given to you. So here you have E is equal to 200I plus 300J minus 50K, and then B is equal to B naught 7.3I minus 7.3J plus alpha K micro Tesla. I'm kind of tempted to put 10 to the negative 6. But anyway, there it is. Okay? Now, what is alpha? And what is B naught? I'll come back to B naught in a minute. How do we find alpha? Okay. You need to know certain mathematical properties in order for you to find alpha. In other words, how E and B are related to each other. Anyone? Well, it is they are orthogonal to each other, correct? Remember we said that. E and B are orthogonal to each other. How do I say that mathematically? If I have two vectors that are orthogonal to each other, how do I represent that mathematically? Well, let me rephrase it again. If I am claiming two vectors are orthogonal, how do I prove that? How do I prove that they are orthogonal? Orthogonality is proven, or perpendicular that is. Orthogonality is proven if you take the dot product of the two vectors, you'll get 0. In other words, in math, if A is perpendicular to B, then E dot B is equal to 0. Here's another one. It's not part of this problem, but make sure you memorize it forever. If A is parallel to B, then A cross B is the null vector, 0. Please memorize that. I mean, memorize it forever. Tattoo it. It's very, very important. Important relationship. If two vectors are orthogonal, the dot product is 0. If two vectors are parallel, their cross product is 0. Okay? So we're going to use the first one. So he's saying it's one electromagnetic wave, so it has those two electric and magnetic waves into it. So if I take the cross product, the dot product, I should get 0. So let's do it. So E dot, B is equal to 0. So let's do it, okay? How does that work? We would go 200 B naught, 200 times 7.3 B naught minus 300 times 7.3 B naught minus 50 B naught alpha, and mu should equal 0. The mu will go to 0, right? Equal to 0. There we go. Is that okay? Oh, the B naught. So what will happen, the B naught will cancel out. You agree with me on that? So we have here, and so I have here with my calculator right there. So I have 200 times 7.3. That's equal to 1460 minus 300 times 7.3 is 2190 minus 50 alpha equals 0. And all I need to do now is to solve for alpha. Hopefully, I am doing it right. This gives me 50 alpha equals to, minus 50 alpha, sorry, equal to 730. So alpha equal to negative 14.6. Okay, there we go. Make sense? Okay, good. Now, how do I find B naught? So now I found alpha. How do I find B naught? Well, there is another relationship that we have studied between E naught and B naught, and that is this one. Again, I told you about it in the beginning of the lecture. see what I'm saying? Or in general, it doesn't have to be not, it's just that. In other words, go back to the vectors that are given to us, this one, those two here, and let's put them in this relationship. It's going to look something like that. What is E? Again, I keep flipping between them. I hope you are taking notes so we don't have to. Okay, here it is right there. I hope, can you please take notes and just write them down, because I don't want to keep flipping back and forth. So, okay, so what is E in this? Remember, this is E vector. What is E? The E is going to be like that. Plus 300 squared plus minus 50 squared. That's E. What is B? Well, B is going to be the same thing. It's going to be, what is it? B naught squared. And then we have here square root of 7.3 squared plus minus 7.3 squared plus what? Minus 14.6 squared. And don't forget that mu squared, that there. You see what I'm saying? And so what I'm going to do, I'm going to take those, this one and this one, and plug them both into here. And don't forget that C. And you do the algebra. I'm going to have you do it. How about that? You do the algebra and you'll end up with this. It's not a lot of algebra, but it's some few steps that you have to work on. And you'll end up with B naught equal to 6.8 times 10 to the negative 2 Tesla. Okay? I think it's a Tesla, not mu. I don't have the unit written here, but I think it's a Tesla. Okay? I'll put a question mark on it. But anyway, you can work it out. Okay, good. The next step, the next part of the problem number 42, he said, what is the pointing vector at this time? What is the pointing vector? Well, how do I find the pointing vector? Well, the pointing vector is just a cross product between E and B. Oops, I don't need that. Part B. So the pointing vector, S, is equal to 1 over mu naught E cross B, right? Okay, let's do it. What is E in this case? Let me just write it down again. Go back to the notes. It is 200I plus 300J. I'm going to do this problem in this part in details. Minus 50K. And then B vector is going to be what? B naught. You know, I'm going to write it as B naught for now. I'll come back to it later. We already know what it is, but we'll just come back to it later. And then parentheses 7.3I minus 7.3J. And then minus 14.6K, correct? There we go. Now I want to take the cross product. How do I take the cross product? There's so many ways to do it. You can use the circle. I, J, K. So you're going to go I cross J is K, K cross I is J, and J cross K is I. That will be legit. You can go through it, but I'm going to show you an elegant way of doing it, okay? You can do it the old-fashioned way, you know, someone who's just taking Calculus 2 or Calculus 3 and finished it. But here is how a professional will do it. You use the matrix method. I'll show you how. So I'm going to get, let's forget about the mu and the B naught for now. We'll come back to them. They just, and the mu as well here, the mu Tesla. So we'll come back to all of that. I'm just going to take the cross product between the E vector and the B without those constant, okay? So here is how. E cross B. You build it up like that. You have a matrix, I, J, K. E cross B, so that's going to be 200, 300, minus 50, 7.3, negative 7.3, and negative 14.6. You got it? And now what you do, let me use a different color. I'll use pink for now. How about that? Okay. So what you do, again, you can learn it. Watch some videos or something. I urge you to learn how to do the cross product, especially 3x3. Like this one is much more elegant and faster and just way better than that. This one works okay if you have two component vector or one component vector. But if you have a 3x3 like that, okay, you got those three components, it's much more elegant to use the matrix method. Okay. All right, so I'm gonna go over it quickly, and you owe it to yourself to learn how to do it. So it goes you start with I, and you eliminate this row and this column, and you work with this one here, and you multiply this minus that. So it's going to be I negative 14.6 times 300 minus negative 7.3 times minus 50. Okay, that's the first part. This is the first component. The second component is negative j. Don't ask me why negative, but it's just the way it works. So you want to memorize it. It's always a negative on the middle one. Now, we're going to do the same thing. Let me change the color. So you say, okay, I'm going to take the j. It belongs to this row and this column. So we're going to take this square right here. This one, this one, this one, this one, this square. Okay, you got it? So that's going to be negative 14.6 times 200 minus 7.3 times negative 50. Okay, and then plus k. What is k? Again, let me use a different color. How about blue? Blue, here's blue. So plus k. So what is k? K is right here. It belongs to this row and this column, so we're going to be working with this box. So that's going to be negative 7.3 times 200 minus 7.3 times 300. There we go, we're done. And then you just do the calculation, okay? You work it out, and then you'll end up with some numbers. And don't forget, sorry, let me go back. Don't forget, I ignored the B naught, so it's just going to be sitting here, and the mu right there, okay? What else did we forget? That's all? That's the only thing we forgot? Oh, and the mu naught. You remember, this mu is different. This mu is different from this mu naught. This mu naught is the permeability of free space, excuse me, and this mu is 10 to the negative 6, okay? So anyway, you take all of that, and then you put them right here. So it's going to be 1 over mu naught B naught and 10 to the negative 6. And when you work out this vector, I don't think I want to do it. You'll end up with some vector, but I'll give you the final answer. And the final answer is negative. You get actually nice numbers, 260I plus 140J minus 200K watt per meter squared. That's the final answer. Okay? Now, I'm not done yet. I mean, I'm done with the problem, but I'm not done with the with the discussion of the problem. Here is a question for you. So I'm claiming that this is my answer. How do you know that this answer is correct? Think about it for a minute. How do you check? How do you check this answer is correct? Here is how you check. That would have been a really nice discussion in class. But anyway, here is how you check. Remember, we said that E cross B is basically S with the constant mu naught. But basically what we said is that E, B, and S are mutually orthogonal perpendicular vectors. What does that mean? It means pick two of them. See, this is S, correct? This is S. And I know the value of E. If I would take the dot product of S and E, what would I get? I'm going to get a 0. Yes? because they're mutually perpendicular. Or if I take the dot product of E and B, I'm going to get 0. If I get the dot product of B and S, I'm going to get 0. Okay? So to check that this answer is correct, watch. So I'm going to go check if S dot E or E dot S, doesn't matter, is 0, and S dot B equals 0. If you get those two to be 0, indeed, this is the right answer, no doubt. Okay? I'm going to try one of them. Let's try the first one, this one, S dot E, and see what happens if we get a 0. Okay? So we said that S here, S dot E, and if you are taking notes down above there, so basically I'm going to be negative 260, 60I plus 140J minus 200K. I'm going to dot it with what? The value of E. Go back to E. E is what? From the notes, or from the problem right there, right here. This is the E right there, right? So it's going to be 200I plus 300K, J, minus 50K. Let's dot them and see what happens. Okay? So what's going to be what? Minus 260 times 200 plus 140 times 300 minus, plus 200 times 50. Is this answer 0? I don't know. Let's see. Maybe I'm lying to you after all. 260 times 200. And this, the first term will give you negative 52000 plus 140 times 300. Answer 42000 plus 200 times 50. I think I can do that. 10,000. Add them up together, and indeed 0. See that? So I know I've done it correctly. See, if I don't get 0, that means there is something wrong here, because the pointing vector is supposed to be mutually perpendicular. Okay? And I think the rest are not bad, so you can work on them yourself. Let me know if you have any questions by posting them under Ask the Professor. Okay? And that's it. Bye-bye.